Да. Hello.
Hello.
Oh, it's great.
Какого тебе удобно? Удобно. Нет, ну тут на камеру. Тебе видно или
Угу. Тогда бери.
Не, не только, там они середине край. За это было просто ранее на другой случай.
Нет, да? Okay. So how many people do we have? Hello, Alex. Do you hear me?
Yes, I can hear you.
Good. Unfortunately, you will not be able to see me because my camera is off.
No problem. Thanks for the invitation.
Oh, thank you very much for agreeing to give this talk. So, Peter, can we start?
I think Peter told me that his microphone doesn't work, so he might not be able to answer.
Just a moment.
Peter, microphone of Peter doesn't work. So he said that we can start. Yes, Peter?
This is
Because
typical,
we're sitting in the similar room.
typical Russian style, I would say. Nothing is working. Okay, so let us begin our today's seminar. And it is a pleasure to welcome Alex Haber, who is now at the Washington University in St. Louis, USA. But his, well, alma mater is Technische Universität, University of Technology in Vienna. And as far as I know, he spent there about 10 years, starting from 2008 as a bachelor, and in 3 years and a half, he got a bachelor degree and became and decided to undertake master program, which lasted for about something more than 2 years. And in January 2015, he got a master degree with distinction. His thesis title is Magnetized Neutron Matter and supervised by Andreas Schmidt. But fortunately, Alexander didn't decided to stop at this moment, at this stage, and he well continued his education as a PhD student at the same university and he graduated, had his PhD defense on in summer 2018, and after that he traveled to the United States, to the Washington University in St. Louis, and he is now a postdoc there. They're working with Mark Alford. And it is a pleasure to me to say that Alex kindly agreed to give a talk at our seminar, which title is written here: Hyperon Biqual Viscosity Neutron Star Matter. It is a pleasure to have this talk at our seminar, especially because we didn't discuss neutron star measures at our seminars at all. It was a shame, and thank you very much, Alex, for giving this talk for us. So let us start.
Yeah, thank you very much for this nice introduction. I'm sorry that my CV is quite boring to read out. I'm going to work on it. And yeah, hello from St. Louis to St. Petersburg. Quite a saintly connection we have here. So I want to talk about, as you heard, about hyperon bulk viscosity in neutron star mergers. And this is based on a paper we put on the archive quite recently. So I just want to make sure, can you see my mouse and my slides? I hope so. If not, please let me know.
Yes, we see your mouse.
Okay, great. Then I can point at things. So yeah, this work has been done mostly in collaboration with Mark Alford, but parts of the results I'm going to present have been worked out by Stephen Harris, who was a grad student in our group and is now a postdoc at the INT, the University of Washington, and our new grad student, Xion Zhang. So I just want to give you a quick outline of my talk. And I hope my introduction is not too long or not too boring. But if there are any questions, please just interrupt me. I try to keep an eye on the chat and on this raise hand feature, but it's easy to miss it. So I want to start with a quite general introduction of why, as a particle physicist, we are interested in neutron stars and neutron star mergers in general, and how a neutron star merger can help us to study dense matter. I want to briefly discuss gravitational waves. So I'm obviously not a gravitational wave physicist, but I want to tell you a little bit how simulations come into play and why they are important, and how they can give us some information about the thermodynamics of a neutron star merger. So you probably all quite know well the temperature and densities we expect in an isolated in the cold old neutron star, but the situation might be quite different in a merger. And then I want to give you a rather thorough introduction to bulk viscosity to give you some intuition, because I think if I do this well, then my results at the end should come as no surprise to you and should be quite obvious. And yeah, in the results section, I want to briefly present our work from Stephen Harris about bulk viscosity in nuclear matter before I'm going to focus mostly on hyperon bulk viscosity, which is the work I have done together with Mark. And here on the right, you already see a picture, of course, not a real picture, just a simulation of two neutron stars merging. So if they get closer and closer, they're in spiral. And at some point, they're going to touch. This is what we call the actual merger event. And during this process, they send out these ripples in space-time that we call gravitational waves that we are measuring right now on Earth. So the motivation is a diagram you've probably seen a couple of times. The so-called QCD phase diagram, the phase diagram of quantum chromodynamics, what some people also call just the phase diagram of everything. And my ultimate goal, at least, and from many people in the community, is to understand this phase diagram of fundamental matter as it's described by QCD and the standard model of particle physics. The problem is this phase diagram is quite complicated. There are various regions and features. So I've drawn a couple of versions here. On the left, you see a very conservative version and with just the most basic features. So the axis here is the temperature, and on the horizontal axis, we have the chemical potential. For a practical purpose in this diagram, you can think of it as the density. And there are two quite distinct regions separated by this long line here. And this is the confined region, the hadronic region that we know quite well, and which is separated to the region where quarks play a more fundamental role in the deconfined region. So this is, of course, a very crude estimate. I've tried to draw a much bolder version, but I have to admit that most of these lines are mostly conjecture. So you see, one of the things we actually do know is that at high temperatures, so when I say high temperatures, I mean, this is 150 MeV. I don't know if you can read this, but 1 MeV corresponds to 10 to the 10 Kelvin. So this is really high temperatures. So if you ask yourself, where do we live, basically? So every kind of temperature we can reach on Earth is for practical purposes exactly around here at T equals 0. So because this is the liquid gas, the line that distinguishes between vacuum and nuclear matter at T equals 0, it's the liquid gas transition, which also has a critical endpoint here. And this is where we live down here. So we know that there's a crossover at high temperatures, low chemical potentials from this hadronic confined phase to the deconfined phase. And we think that there's a critical endpoint, but we haven't seen that yet. And there are various superconducting phases. We have nuclear superfluidity down here. We think this should be a nuclear superfluid, and then various kinds of quark superfluids.
Sorry, may I ask a question?
Sure.
Yeah, when neutron stars merge, in which part of this diagram they can be available and for how long?
Yeah, great question that I'm going to answer on the next slide.
Good.
So the question that was already asked and is connected to that is, of course, how can we attack the QCD phase diagram? How can we learn anything about it in the first place, and how did I come up with these lines? And in principle, an investigation of this phase diagram can always be experimental or theoretical, but in reality, it's always a mix, right? And theory is kind of worthless if you don't have any experiments to back it up, and the other way around, you observe a lot of things, but you need theory to understand the observations. And as I said, this is a huge range of thermodynamic parameters. Of course, I've drawn it in a two-dimensional way with temperature and density, but there are other parameters one could think about. Of course, neutron stars, this is for symmetric nuclear matter, same amount of neutrons as protons, but neutron stars have way more neutrons than protons. That's why they're called neutron stars. So one could add another axis with isospin and just see how this phase diagram behaves at a higher neutron fraction. One could think about how magnetic fields, and as I said, the particle content is quite different. There might be hyperons somewhere hidden in here, and here we have quarks, and here we have hadrons. So the question was, how do we attack and know anything about this phase diagram? Well, there are various possibilities. So at very high chemical potentials and densities, somewhere up here, let's say, we can use perturbative QCD, which really allows us from QCD directly without using any further models to compute various quantities. Problem is there's not really a laboratory or environment on Earth or on the sky that we know of where perturbative QCD applies directly. So it's hard to test it. So the chemical potential and temperature needs to be much larger than lambda QCD, which is this typical scale of QCD here, this transition temperature.
And merging neutron stars, they will not show us anything about this region as well, yeah?
No, we don't think so.
Mm-hmm.
So you need really high chemical potentials and temperatures for perturbative QCD to be applicable. One caveat might be that if you have a strong magnetic field, the QCD coupling also becomes smaller. So maybe if temperature is high, density is high, and high magnetic fields, we might be able to learn something about it, but I'm not sure if this is really the case.
Yeah.
Okay, to go back to the diagram, so you see here I've drawn this as this shape here at small chemical potentials and nearly arbitrary temperatures. We can use lattice QCD, which is a numerical implementation of QCD on a computer. But this is plagued by the so-called sign problem. So the chemical potential has to be much smaller than the temperature. And of course, down here where we live, we can apply, I say, ordinary nuclear theory, the kind of nuclear theory we all learn at university. And okay, to go more to the experimental sides, we can also do nuclear experiments, but more interesting for the QCD phase diagram probably is this blob I've drawn here and called particle collisions. So this is where all the colliders are operating, like the relativistic heavy ion collider in the US or the LHC in CERN in Switzerland. So they test this region, and we have not seen this critical endpoint, but there are new experiments coming up in Germany and in Russia where they are aiming to probe this little higher density, and maybe we can find the critical endpoint, this point here. But more interestingly for this talk, what I want to focus on are neutron stars, which I've drawn here. So I've said before, neutron stars, they have a typical temperature of keV. So they cool down really quickly after they are formed in a supernova. So they're also down here. But neutron star merger are quite interesting in that sense because they probe much higher temperatures and maybe also higher densities. So they form this rather bigger blob and might explore really quite a range of different kind of matters and temperatures.
And for how long?
So I'm going to talk a little bit about this time scales later. Of course, how long the merger survives itself depends on the masses of the initial stars. So there might be the case that it promptly collapses to a black hole, but what we believe that we have seen so far is a star that survives in the millisecond range, so maybe 100 milliseconds or so.
Mm-hmm.
So I'm gonna show this in a couple of slides. Okay, so why are neutron star mergers so interesting for us? Because, as I said, this is a completely new way to tackle the QCD phase diagram. It's not just about different temperatures and densities, which is always nice to find a new region, to test a new region in the phase diagram. But we can not only observe them just by electromagnetic radiation, this is all what we've been able to do before for old isolated stars, but we can also see gravitational waves. And this is really a completely new window into the sky that we can use. So it offers a complete new way to study dense matter, might it be a nuclear matter, quark matter, or more exotic matter. And I claimed before that merger test matter densities up to several times saturation density. So saturation density is the density inside a nuclei, for instance. It's roughly saturation density. And tens of MeV of temperatures. The problem is learning something about dense matter directly from gravitational waves is quite challenging, but it's a unique opportunity, so we should really try it. So how do we actually measure gravitational waves, and how do we get to learn something about it? So you see an actual image here of two detectors from LIGO in the US, in Livingston and Hanford. And you see this long arm here. So this is a laser interferometer. You have two arms perpendicular to each other. And these arms are 4 kilometers long. And if a gravitational wave passes through the plane of these two arms, then these arms will move and the distance will change relative to each other. And you can see this as an effect on the laser light. The problem is, so if a gravitational wave passes through it, these 4 kilometer arms change length by roughly the size of a proton. So this is very, very little. And the signal consequently is very noisy. You can easily imagine that a truck that drives by makes the mirror shake much more than a gravitational wave ever could. For the next detectors, they are worrying about clouds passing by, that they're gonna distort the mirror more than a gravitational wave. So this is one of the sources of noise they have to deal with in these detectors. So the point I want to make is we cannot just look at the signal we're getting from the sky. We have to have some input, and this input comes from numerical simulations. So we set up the neutron stars on a computer and try to simulate it before and see what the waveform will look like. So we have 2 confirmed successful observations, GW170817 of a neutron star merger and GW190425. If you have been wondering what these numbers just mean, this is gravitational wave event observed on the 25th of April 2019 or 17th of August 2017. And you see here the actual plot, the signal from GW170817 measured in Hanford and in Livingston. And you see the actual strain, so the movement of the arms. And down here, it's compared to the wavelet, the template from the gravitational wave simulations. And we can use these simulations to learn something about the thermodynamic environment in a merger. So I want to briefly discuss what these simulations take into account and how do they work. So basically, they are a mix of numerical relativity and hydrodynamics. So they take into account, of course, the backbone of this simulation is Einstein's general relativity. So the basis is we are evolving space-time, the space-time metrics throughout the merger using Einstein's equations. So for black holes, that's mostly all you have to do, but neutron stars, of course, more complicated because it's not just a deformation of space-time. There's actual material and matter involved. So we have to use relativistic hydrodynamics. And the matter that's making up these stars is more or less modeled as a perfect fluid. So there's no true viscosity in most of these simulations. But of course, you're working on a finite grid, and energy conservation on a finite grid is always challenging. So you're basically leaking some energy during the evolution of the merger just due to numerical mistakes and numerical errors. So this is what people call numerical viscosity, because basically if you lose energy, this is some kind of viscosity. Another input is the equation of state. So the equation of state is quite important for neutron stars. This is something everybody is after. So this is how the pressure behaves as a function of the energy density. And the equation of state describes the behavior and the composition of matter. So in these merger simulations, it's often just a simple model. So it's not really based always on nuclear physics or fundamental microscopical physics. Of course, they have to model electrodynamics to some extent because magnetic fields can influence the development of the merger quite a lot. This is known as so there can be effects where the magnetic field grows drastically in the merger and can also lead to some form of viscosity. I think this is what people call magnetic braking. And neutrino transport plays quite an important role, but the behavior of neutrinos really drastically depends on temperature. So we need to know a little bit about temperature, but I'm going to talk about neutrinos briefly on a later slides. So to summarize that, simulations are basically a combination of numerical GR and relativistic hydrodynamics. And I hope I didn't give the wrong impression that I think these simulations are too simple. They're technically really hard and quite sophisticated, but they necessarily neglect a lot of physics. So we cannot just throw the entire Lagrangian for the standard model of particle physics at these merger simulation groups and tell them just implement everything. So we need some improvements. They're quite important, especially, so right now we've seen the inspiral, so the early ages of the merger. So what I've shown here, this is before the stars actually touch. Right here on the right end, they start touching, and the frequency and the signal frequency gets too high, the signal is not high enough. So we haven't seen the actual post-merger event. But this merger event then is really driven by fundamental physics. So if we want to learn as much as possible from these future observations that we're hoping to get, we really need a better understanding of the fundamental physics taking place there, and we need to implement it into these simulations. But the big question is, where should we start? So I want to talk now a little bit about the thermodynamic environment, and it's a little bit a catch-22, but it's the best we can do. So what you see here in this plot is the result of one of these merger simulations. And on the y-axis, so this is going to be a movie, I'm just going to explain it, what you're going to see. On the vertical axis, you have temperature ranging from 0 all the way up to 80 MeV, which is really hot. And this triangle here is going to follow the highest temperature. And on the other axis, you have density as a function of nuclear saturation density, whereas this square is going to track the highest density, and this is going to be the evolution of the merger. So t equals 0, where the movie will start, is when the stars touch for the first time. And the color coding tells you a little bit about where in the merger this region is located, but it's not that important right now. I'm going to have a better plot at the end. So you see right at the beginning, this is now the stars have touched, and you have quite a violent change in temperature and density. At the beginning, it's rather arbitrary, but then there forms a kind of structure that Marx likes to call the St. Louis Arch. If you have ever been to St. Louis, we are quite proud of our symbol, of our great monument, Great Arch. This is roughly what it looks like. And you see the highest temperature in this simulation goes up to roughly 50 MeV. Some simulations claim that the temperature reaches up to even 100 MeV. And the maximal density, the density maxes out somewhere between 4 and 5 times saturation density. So this plot is of course not produced by us. This plot is produced by Matthias Hanauske from the Risola group in Frankfurt, which is one of the big neutron star merger simulation groups.
And there is no magnetic field, yeah?
I think these simulations take magnetic field into account, they do.
Take magnetic field into account. Well, and the equation of state is nucleonic one?
I think it's just epsilon to the power of some. It's just one of these rather simple equation of states.
Yeah, not nucleonic, but well, I understand. Thank you.
Polytropic. That was the word I was looking for. Yeah. So what I want you to take away from this plot is what you see. There's a significant spatial and temporal variation in temperature, and this immediately might lead you to think that what about thermal conductivity? Does thermal conductivity play a role? And you see, this was hidden in the color coding. It's not easy to see, but the fluid flow velocity changes quite a lot. So it's not a uniform flow. So this immediately makes you think, what about shear viscosity? And I'm going to show you another plot here. And what you see here is now, so the horizontal axis once again is in milliseconds, the time after the stars touch, 0 here. And now you see for the first time the time scale that we've been talking about. So this is now for 20 milliseconds. So you see here the density variation in the lower panel. And you see after 20 milliseconds, everything roughly dies down. So these various lines correspond to various different fluid elements in the star, various different places, so to say. And this oscillation never truly completely died down, but this might be related to some numerical errors. So it's really what we want to focus on is on these early stages here. You see really quite strong density fluctuations. They seem to have a frequency of roughly 1 kilohertz. And especially in these first 5 milliseconds, you see large amplitude oscillation. The amplitude reaches up to 50% of the background density. One complication that one might have to think about in the future is, you see these oscillations in the later stage, they are around roughly a constant average density, but this is certainly not true in the early ages where the average density steeply increases in the first 5 milliseconds.
And what is the mass which is involved in this event?
Sorry, what do you mean by what do they mass?
The mass of the star. There are 2 stars, yeah?
Yeah. I think this was for 2 canonical stars of 1.4 solar masses.
1.4. So 1.4 plus 1.4 will be 2.8, yeah? So,
yes.
But something will be lost during the gravitational wave emission, yeah?
Yes, I don't know exactly what the remnant, how massive the remnant was in this simulation. But this simulation is certainly one that collapses to a black hole at the end. So it's not a supermassive neutron star. So these neutron stars, of course, you have differential rotation after the merger, which helps you keeping a more massive object alive. That it can be more massive than an isolated old star that has no differential rotation anymore.
I see.
On the upper panel, you see the temperature variations again. We've talked about the temperatures before. So the question now is, I've brought up a couple of things, right? Thermal conductivity, shear viscosity, bulk viscosity as possible new things to look at. But the question is, which of these processes operate on this time scale? So if shear viscosity, let's say, takes like years to have any influence of the merger, we really don't care anymore. The merger is gone by that. So we have to ask which processes operate on a merger time scale, so in the millisecond range. So as I said, this is the premise. We're looking for dissipation mechanisms whose equilibration time is below 20 milliseconds. And transport is quite interesting because it's often a better discriminator for the particle content in the phases than just the equation of state. So in neutron stars, we can, for instance, if we measure the mass, we get some information directly from the equation of state. But many different equations of state lead to quite similar masses. But transport is much more sensitive to particle content. So transport is very interesting already in normal stars, but in a merger, this is still true. So in the first paper, Mark Alford and collaborators from this Frankfurt group in the PRL in 2018 have calculated some estimates for these quantities for shear viscosity, thermal conductivity, and so on. And I just want to summarize the conclusion here. So for thermal equilibration, they found it might play some role if neutrinos are trapped. So I mentioned that before. So in an isolated star, in a cold star, neutrinos are free streaming. Their mean free path is so long that they just, if they are created, they leave the star without any scattering events. Above 5 MeV, the mean free path becomes of the same order of magnitude as it becomes roughly the size of the star. So there might be a couple of scattering events, and above 10 MeV, so these are just rough estimates, of course, above 10 MeV, neutrinos are truly trapped and form a Fermi sea and everything. The other thing that they need for thermal equilibration to play a role are short distance temperature gradients on a roughly of 100-meter scale. The problem is most simulations we have don't have this kind of resolution yet, so we can't even tell if we have these kind of temperature gradients. For shear viscosity, there's this very similar conclusion, but for bulk viscosity found that it might potentially be quite important. So the question we have to ask is bulk viscosity large enough really for a significant damping of oscillations? So this is our criterion. We need some kind of time scale to compare to this 20 milliseconds. So we define a time scale that basically tells us, is the energy of an oscillation, does the energy die down significantly of an oscillation?
And what about turbulent viscosity? Viscosity which is associated with small scale turbulence.
Yeah, that's a good question. So unfortunately, we approach the problem always from a microphysical point of view, and turbulence and all these phenomena are really a question for the simulation groups. So I know that this shows up from time to time, but right now the grid scale I think is larger than 100 meters. So I'm not 100% sure if they can really resolve turbulence on a relevant scale in their simulations.
Yeah, thank you.
Okay, I've mentioned bulk viscosity, and that is quite important. So in the next 3 slides, I really try to give you a good estimate, a good understanding of what bulk viscosity is. So I think bulk viscosity becomes quite easy to grasp once you think of it as compression dissipation. So you have some sort of fluid element here, and we start to compress it with some form of harmonic motion. And if there's some internal quantity in this, so let's say there's something that depends on the pressure. For instance, in a neutron star, we can think of the proton fraction, right? If the pressure increases, normally the proton fraction will change, and if we decrease, it will change back again. And this internal quantity might need time to equilibrate. It's not always intermediate that the proton fraction can change. So in this case, the density, and therefore also the fluid element volume, gets out of phase with the applied pressure. So dissipation, you can always think of the easiest definition you can have that we all learn in school, at university, is just PDV work, right? And if we formulate it like this, we want to integrate it over a full period of this oscillation. then we can easily see what I mean by that. So if we look down here, we draw some sort of harmonic oscillation. So we have a harmonic change in pressure. And if everything is in equilibrium and it's as supposed to be, then if the pressure is at its maximum, of course, the volume, which is this dashed blue line down here, the volume should be at its minimum, maximum pressure, minimum volume. So let's say this is some sort of sine function, then the volume is the negative sign. Then the change over time, dv dt, is of course a cosine. And this is quite obvious. You integrate a sine times a cosine, so this is 0. So in a PV diagram, this is just you go back and forth this straight line if you have multiple cycles of compression. But let's say there's some kind of, let's say, proton fraction. It takes some time to equilibrate. So what we mean, the pressure is maximal here, but the volume is not yet at its minimum, right? It takes a little bit of time. There's some sort of phase lag in here. And then there's an offset between the pressure curve and the dv dt curve. So we get this kind of hysteresis here. And the dissipated work is just the area under this, in this curve. So this is when we have dissipation in some form of bulk viscosity. So in a more thermodynamic description, you see this compression of a fluid is just the dv term. So this is the fluid velocity. This describes the compression of the fluid, and this is the energy density that changes. And you see this coefficient here is what we call the bulk viscosity. So to make this a little bit more specific, so we say, let's say we have a piston moving up and down in a cylinder here. So you see this is a piston cylinder, and in here is either some sort of gas, but we might think about some nuclear matter that's in here. And what I want to get is why bulk viscosity is a very resonant, frequency-dependent phenomenon. So let's say we have some form of harmonic compression with a given frequency. So if we go up, the piston goes up, then we're going to do some work on the gas or on this matter. And if on the way down, the gas will provide us with some work done by the gas on the piston. So if the gas is always the same and nothing changes, we have no net dissipation. Of course, we can run stuff like friction and so on. But basically, the work I put in on the way up, I get back out on the way down. But let's say we have nuclear matter. We know that this nuclear matter reacts to a pressure change, as I said, for instance, the proton fraction that I call XP. And this proton fraction changes via a weak process. So this is, in a lab, you would just call this neutron decay. In neutron stars, in a medium, you call this the direct Erker. So you see you have a neutron, and it decays into a proton, an electron, and an antineutrino. And of course, if we wait long enough in a star and we have no oscillations, there will be some sort of equilibrium, and we call this the beta equilibrium. So in this case, the rate back and forth, this is why we have a double error here, are exactly the same, and therefore the proton fraction stays the same. But if we now compress this piston, we're pushing matter out of beta equilibrium, and it takes some time to get to the right proton fraction, right? And this time now depends on the difference between this forward rate and the backward rate. So if neutrons decay faster than protons can catch electrons again, we're going to change the proton fraction. And we call this difference of rate delta gamma. And now we can look at three very distinct cases. And let's say this re-equilibration time is much, much smaller than the external frequency. So what this means is that basically the matter never really reacts to the change in pressure. The frequency, it's just too fast. So the proton fraction is always constant. So basically I'm always out of equilibrium. Let's say I'm starting at chemical equilibrium. The proton fraction will always be the same. So as soon as I start compressing, I'm out of equilibrium, but I'm always staying at a constant proton fraction. So I don't get any bulk viscosity. I always have the same, let's say, gas on the way down and up and down. In the very opposite case, where these reaction rates are basically instantaneous, the proton fraction is always correct. So what I mean by that, if I give you the equation of state and tell you the pressure, you can use beta equilibrium to compute the proton fraction. So the matter is always instantaneously in equilibrium, and I also get no bulk viscosity. I'm sorry, I need to quickly plug in my computer. I'm very sorry, I ran out of battery. I hope you can you see me again and hear me again?
Yes.
Okay, sorry about that. So yes, so we discussed case 2 and 3. Let's look at this middle case. So in this case, if the equilibration rate and the external frequency are compatible, then the proton fraction basically becomes history dependent. I cannot just tell you anymore the equation of state and the pressure, and you cannot compute the proton fraction from it. You have to know, are we on the way up or down, or how often did we already compress? So we get some kind of maximal bulk viscosity, maximal dissipation in this case, because we're not dealing with the same kind of matter up and down. So just to summarize that, the bulk viscosity is therefore a resonance effect. We have to really find the perfect frequency between two competing timescales of frequencies. We have the driving force, which is the external density oscillation omega, and the response, which is the internal reequilibration gamma. So if we compute the bulk viscosity, it's then proportional to this fraction of gamma, which is this internal reequilibration time, and the external frequency. So if you see at the plot, this schematic plot down here, you see on this end, the reequilibration is just way too slow. Matter never really equilibrates, but once this internal reequilibration time really hits the frequency, I get the maximum bulk viscosity. So this is bulk viscosity plotted as a function of this reequilibration time gamma. And on the other hand, it dies down again if gamma gets too fast. So the question, of course, is what drives this reequilibration? And there are various possibilities, of course. The strong interaction is always too fast. So if we're talking about these millisecond timescales, strong interactions are just too fast for some form of sizable bulk viscosity, but they're still quite important because they lead to thermal equilibration. So this allows me to assume that in a merger, baryons and so on, they are still in thermal equilibrium, and that their distribution in phase space is described by a Fermi-Dirac distribution. Electromagnetic interactions are also too fast, but I mean, I've already hinted at that. Weak interactions are quite a good fit, because we know that particle lifetimes can range from nanoseconds to minutes. So free neutron decays in roughly about 940 seconds or so. And these weak interactions, they equilibrate particle content. So this is what I wanted to say about bulk viscosity. We can, of course, now discuss various types of bulk viscosity in a neutron star merger, because there are different kinds of matter. And I want to briefly start with nuclear bulk viscosity. This has been computed by Mark Alford and his grad student, Stephen Harris, as I mentioned before. And they separated it into two papers. There's the neutrino transport matter regime, so for temperatures roughly below 5 MeV, mega electron volt. And they really find that damping times can be in the millisecond range. So I've used this plot from his paper here. And this is for two different equations of state. We can just focus on one of them, let's say on the left. And what you see here is a contour plot for various different, in the plane of baryon number, density, and temperature. And you see these contours, the innermost one here correspond to 10 milliseconds, and 25 milliseconds, and 50 milliseconds, and then they grow. And now with the explanation of bulk viscosity before, you immediately see what's going on here. So these rates, the internal rates, this is really for directly modified ergo, so for neutron decay basically, the rates depend on temperature. So down here we have very long dissipation times, 10 seconds. Why? Because bulk viscosity is very low, and bulk viscosity is low because the rates are too slow. So we have to increase temperature, we go up and find this resonant maximum. So we start here and go up here to this maximum. And this is when we hit the shortest dissipation times. And then, of course, if I increase temperature further, I get a kind of symmetric plot because the temperature now is too high and the rates are too fast. So bulk viscosity is low, dissipation times are high. But you also can see they also depend on density. Of course, if I basically increase phase space, I have more neutrons, the rates will always grow. And so the rates are ideal at rather low densities, but they don't depend that strongly on density. You see this is rather flat down here. Once you hit 10 seconds, it's a rather flat curve. And this is for an external frequency of 1 kilohertz, as we talked, as I said before. On the other hand, in the neutrino trap method, this has been calculated by Mark and collaborators in Frankfurt, Armin Sidrakin and Arus Harutinian, and they find that it's probably negligible, so the time scales are larger than these 20 milliseconds we've been talking about before. I want to rather focus on hyperonic bulk viscosity. This is the part I've been working on mostly. So why do we want to look at hyperons? I've just cited one paper here, a rather old one. Of course, many of you have worked on this topic. So the motivation is in cold matter, we already have some form of sizable bulk viscosity. So there's some form of potential, but we now have to see how bulk viscosity of hyperons behaves in this higher temperature regime. Of course, many people don't like the idea of hyperons in neutron stars. This is what's called the hyperon puzzle, because hyperons are softening the equation of state, so they would lead to rather light neutron stars. But even if you don't like the idea of hyperons in isolated stars, in a merger, of course, we have higher density and temperatures. So we either might reach the critical density. So you need a critical density, that a minimal density you need to reach to have hyperons in a system. But this is only true at vanishing temperature, right? If we have some finite temperature, then there might be some thermal population. There is some kind of thermal population even below this density onset. So in these high temperatures of 50 to 100 MeV, if hyperons exist, they should really show up at this point. Of course, there are other things to look at, like leptonic bulk viscosity, which is rather small at low temperatures. Bulk viscosity in quark matter might be very interesting to look at in the future, where color superconductivity might play still a role at these temperatures. And one should also revisit nuclear bulk viscosity. The results are shown before at finite magnetic field, which might change things a lot because there's no direct Urquhart threshold. Or looking at medium corrections like Peter Stern has started to do. Okay, I want to start talking about hyperonic bulk viscosity. So in order to do this computation, you need some form of creation of state. So we came up with basically our own model toy equation of state. It's phenomenologically not the best equation of state, obviously, but it's numerically quite easy to handle. So it's based on a relativistic mean field model with nonlinear sigma and omega meson terms. It includes sigma minus and lambda hyperons on top of neutrons, protons, electrons, and muons. So you see the particle content here at 2 MeV. So this is just the fraction of the various baryon species as a function of density. And you see the first hyperon to appear at roughly 1.8, 1.9 times saturation is the sigma minus. So the sigma minus helps to establish charge neutrality. So you always want charge neutral matter. So you have protons, you need electrons and muons to offset this charge. And the sigma minus hyperons help to do so. So they appear before the lambda hyperon in my equation of state, although the lambda is a little bit heavier than the sigma minus. For the nuclear couplings, we use the so-called Pika-1 parametrization, and we then just add hyperons to it by fitting the hyperon couplings to the hyperon potential. And basically the goal was to look at a spectrum of a way more complicated equation of state like TDME2 and reproduce a particle spectrum with this simple relativistic mean field model. So we only get maximum neutron star masses of 1.88 solar masses. So we partially checked with one of the equations of state. Also, your group has been investigating in the past the GM1 prime B with a much higher maximum mass of neutron stars. So an old neutron star with this equation of state can reach up to 2.02 times the solar mass. And the point is there are some different hyperons. There are the psi hyperons that appear, and the lambda is actually the first one to appear. So we did some checks, and I'm going to show you these in a couple of minutes. So how do we actually compute hyperon bulk viscosity? What do we do? So as I said before, we need some kind of particle content that changes due to weak interaction. In the nuclear case, this is just neutron and proton fraction and via beta decay. So here we have many more, since there are many more kind of particles with all these hyperons, we have to limit ourselves to some rates here, some processes, and all processes we're looking at change strangeness by 1. So in case you don't know, a hyperon is just a baryon like a neutron and the protons are with some strangeness in it. So there's at least one strange quark. And in these processes, you see strangeness always changes by 1. There's no strangeness here, and the sigma minus has 1 strange quark, and otherwise just up and down. So we take into account 4 different processes which all change strangeness by 1. N plus N goes to proton and sigma minus, neutron plus proton to proton and lambda. And of course, in chemical equilibrium, once again, these rates are the same back and forth in both directions. And then there's neutron plus neutron goes to neutron plus lambda. And in some sense, the opposite of this, lambda lambda goes to lambda plus neutron. So how do we compute these rates? So the basic integral we have to solve is a phase-space integral. So there's the matrix element squared, which tells you the probability basically of this decay. And you have to integrate, so you have 4 particles, right? All of them have a 3 momentum, so you end up with basically a 12-dimensional integral over the full momentum space. And this is all modified by, multiplied by Fermi-Dirac distributions, which tell you the probability of having a neutron in the incoming channel, a second one for the second neutron, and the probability of having some space to create a proton and a sigma minus on the other side of the reaction. And of course, we need to have energy momentum conservation in all of these reactions. So normally, what people do now is to use the Fermi surface approximation. So in the Fermi surface approximation, what people assume is that neutrons at t equals 0, this is a true statement, an exact statement, neutrons, protons, all the fermions going to build up a Fermi sphere with a very sharp and a distinct edge. And the size of this sphere, the maximum momentum we have, is what we call the Fermi momentum. So since all of the states down here are occupied, and the only states that can contribute, which can contribute to these rates, are the states directly on the Fermi surface. So instead of having to deal with all this integration, all this general momenta, we can just say everything is on its Fermi surface and the calculation gets much easier. The problem is at higher temperatures, and I try to illustrate that here, this Fermi surface gets blurred, and this blurring is roughly the temperature divided by the Fermi velocity. So some states get some temperature kick basically and go up here, and you see there are states now further out occupied, so you don't really have a sharp Fermi edge anymore. And since we're dealing with higher temperature in a merger, what we do is instead of using the Fermi surface approximation, we deal with this fully 12-dimensional integral. Parts of it, of course, you can do analytically, but you still end up with a 5-dimensional numerical integral you have to solve. And this gives us quite an improvement, especially at higher temperatures where the Fermi surface approximation is not valid anymore. Also for the dispersion relations, we use a fully relativistic calculations. This is quite important at higher density when the matter becomes rather relativistic, especially if you take into account that the baryons have an effective mass in the medium, which gets smaller and smaller with higher temperature. So how do we get the matrix element? This is this fundamental ingredient in here. So we use a combined weak strong vertex. So this is the Feynman diagram here. This is maybe not super easy to understand. So I tried to draw a quark flow chart on the right here. So forget about this diagram for the moment. These 2 diagrams on the left belong together. So what's happening is here you have, I've been drawing this for one of the rates. For the first one, neutron goes to proton to sigma minus. We read it from the left to the right. And you see we have 2 neutrons here and the proton and the sigma minus. So inside the neutron, we have some sort of weak decay, and we're creating a strange quark out of the up, and this down turns to a strange via this W boson exchange. So this is the weak interaction taking place, and we can create some intermediate off-shell state. But if you just look at the quarks, DSU is not what a sigma minus quark is. It's a sigma minus baryon hyperon is, this is DSD. So by using some kind of meson exchange, so this is a strong interaction taking place, you can sort of say rearrange the quarks and ship down the up here and bring up and down, so you get a sigma minus here. And this combination of this strong interaction and this weak interaction is what we combine in this weak strong vortex. And of course, many of you have been working on this, and this is this paper I've cited here, which I really liked a lot to read. It was very thorough and well written. So this is what we call one meson exchange. In most cases, it is a pion. For the last process here, it's actually a kaon. That's why I call it one meson exchange.
Yeah.
So this is in opposite to a purely contact interaction. So you can, of course, imagine that instead of a strong interaction here, you just exchange a W boson directly and just let the weak interaction do its job. And at these energies and densities we are talking about, normally you can ignore the W boson. The mass is so high that we can just integrate it out and have a simple contact interaction. The problem with that is, so there is a contact interaction matrix element for the 1 and 2, but for 3 and 4, you would have to exchange. You see there's no charge involved here, so you would have to exchange a neutral Z boson, and this flavor change in neutral currents, as they're called, are highly suppressed by what's called the Jim mechanism. So you can't really compute it in a contact interaction, but these are quite significant, so you have to take them into account. And you can do that by using this one meson exchange picture. So I can finally show you my results. So what you see here are now the rates for these 4 processes, 1, 2, 3, and 4. So these are these 4 different processes I've been showing you before. This is just at one certain temperature at 5 MeV. And on the horizontal axis, you see the density as a function of divided by the nuclear saturation density. And you have the rates here. And there are quite some interesting features. So first, what you might expect is that the 4th rate that includes more hyperons is, firstly, it's shifted to the right, because in my equation of state, the lambda hyperon appears later than the sigma minus. So this has its 3 lambdas, so it's much lower here. They also all kind of bottom out at the max out at the roughly the same value and become rather flat. They're not strongly density dependent here anymore. But if you remember, the hyperon onset for the sigma minus is roughly here at 1.8. So below that, at T equals 0, you wouldn't have any hyperons anymore, so you would have to cut it off here. But of course, as higher temperatures, as I said, we have this thermal population of hyperons, which still give us a rate, but the phase space is exponentially suppressed, right? So the rate are really spanning orders of magnitude and quickly dropping down. But if you remember what we said at the beginning about bulk viscosity, the rates need to be ideal. And I'm going to show you later that the rates are kind of too high in this regime. But since we have this exponential suppression and quick drop down due to this just thermal population of hyperons, we kind of guarantee to find some sort of region where this rate will actually match the external frequency of 1 kilohertz that we're looking at.
Sorry, may I ask a question?
Sure.
What about these oscillations, weak oscillations of this black dashed curve?
Here?
Numerical.
Yeah, this is numerical, yes. So since this is a 5-dimensional integral over Fermi-Dirac distributions that are quite sharply peaked at the end, it's numerically quite challenging. So you get some kind of noise here, yes.
I see.
So let's look at the plot at the right. So this is just the sum of these 4 rates. So we have to add all of them up. They all change, they all equilibrate the same chemical potential. It's all the strangeness chemical potential that's equilibrated. And this blue line you see here is really just the sum of these 4 rates here. And it, of course, shows roughly the same behavior. What's interesting is I've compared it here to the Fermi surface approximation for the, also OME stands for one meson exchange. So this is the one meson exchange channel I've been explaining before. And what might be surprising or interesting to see is that the Fermi surface approximation overestimates the rate, especially at low densities. So first off, at higher densities, you always expect the Fermi surface approximation to match the full phase space integral, basically because if you increase this phi a lot and keep the temperature constant, this blurring basically don't plays a role anymore. But the point is, yeah, as I said here, the Fermi surface approximation takes away this blurring, right? So you get less phase space, so you would expect the rate to drop. So this is just for people who have worked on that. So in the computation of the Fermi surface approximation, you always assume that the temperatures are small and the integral boundary for the energy integral is mu over t. So for small t, this is basically infinity, so you integrate from minus infinity. So at higher temperatures, this approximation gets rather bad and you start to overestimate the phase space because of this approximation, and this overpowers the loss of the thermal blurring you have in the Fermi surface approximation. Another thing I want to point out is the contact interaction, which I have to admit I also computed. So in order to be able to compute this analytically, you make some further approximation. Basically, you are in a super ultra non-relativistic approximation where all momenta are zero. And this underestimates the rate quite a lot. But also the contact interaction channel, this is something you have shown in your papers. Even if you do it in a better way and take the angle average matrix element, I think, then it's still the much slower rate compared to the one meson exchange. So the one meson exchange is really the way to go. But also I want to point out, of course, the Fermi surface approximation breaks down once you don't have, you're not above the critical density anymore. Once you only have a thermal population, you don't have a defined Fermi surface because you don't even start to fill it up. There's just a thermal population. So if you want to get this drop down here, you really have to include, have to solve the full 12th dimensional integral. I said before that we've compared it to another equation of state, the GN1 prime B, and in this equation of state, the lambda hyperon is first to appear. So this is rate for one process. I cannot compare all the rates because there are no sigma minus hyperon at these densities that are relevant for us. So I've picked one, which is n plus n goes to n plus lambda in this case. And as the lambda hyperon appears at a higher density in this equation of state, which makes sense, this is why the equation of state is stiffer and you can support heavier stars, you see that this rate is shifted. But other than that, it basically shows the same behavior. It tops out at the same maximum rate, and it also spans its many orders of magnitude. So we kind of expect a comparable result for the bulk viscosity as well for different equations of state. Of course, this ideal regime where the external frequency hits this re-equilibration rate gets shifted by, especially in density, if you use different equations of states, but otherwise we expect it to be rather the same. So this was just a quick plot to show you the different equation of state. I'm going back to the equation of state we've been using, what we call pk1 plus h. And now we can finally compute these re-equilibration rates gamma. And this is probably the most important plot for now. So we said we assume these external oscillations that push the fluid element out of chemical equilibrium. And we now need to calculate this re-equilibration rate gamma that goes into the bulk viscosity. And it's computed from now. So if we push it out of equilibrium, these back and forward rates of these four processes, they're not the same anymore. So the difference between these rates is what we need to compute here. Then there's just a minor detail. We use a linear approximation. So this might break down if the amplitude of the oscillation gets really large. This is something to look at in the future. And of course, we need to compute the susceptibilities from the equation of state. So there is some input from the equation of state that goes into it. So what you see here on this plot is now this equilibration rate gamma as a function of density again, and I've plotted it for various different temperatures, the blue line being 3 MeV all the way up to 50 MeV, and the green line is 5 MeV. So these 3 lines down here are the lowest temperatures. And this vertical line is, in my equation of state, the onset of the sigma minus. So you see what I've shown you before, that the rate basically is not strongly density dependent anymore above the onset, slightly going up. But below the sigma minus onset, you get this rapid drop. And the horizontal line I've been drawing here is the external oscillation of 1 kilohertz. So when this line intersects here, these two lines intersect, this is where we get the maximum bulk viscosity, because these two frequencies, these competing frequencies, are now matching. And you see that for up to 5 MeV, I see some sort of intersection here. So we can basically already from this plot read off the ideal density, and for each temperature where bulk viscosity will be maximal. But we also see, as I said, it's too large here. So we really need these thermal populations. Maybe a quick note on why we chose this parameter range. So basically below 2 MeV, nuclear and hyperonic superfluidity might play a role, and this is something we ignore. So we don't compute it for lower temperatures, but it also becomes much more difficult to do the numerical integrals, of course. And at higher densities, at some point, other hyperons also might appear. So we cut it off at 4 times saturation density. But yeah, as you see, bulk viscosity will be the biggest here in this regime, so we really don't have to worry too much about the right end of the plot. And of course, at lower densities, at some point, matter is not homogeneous anymore. We expect these nuclear pastel phases or the crust of a neutron star to come in. So now that we have this reequilibration rate, we can use it to calculate bulk viscosity. This was the goal at the end. I mean, and this was the title of my talk, right? So you see here the bulk viscosity. Let's start on the right. This is above the sigma minus. So I say we start in the left panel, but on the right of the hyperon onset, this vertical dashed line. And you see, if I increase the temperature from 2 MeV to 5 MeV and all the way up to 50 MeV, what I get is the bulk viscosity becomes smaller and smaller. So this is absolutely what we expect. We see the rate is already too fast for 3 MeV. The rate roughly grows with T cubed. So if I increase the temperature further, and the rate will just get faster and faster. So this match is worse and worse. I go down the right side of this peak that I've been drawing at the very beginning. So bulk viscosity goes down. It slightly changes with density. So the interesting part is below the hyperon onset, where we have this exponential suppression and this quick drop of the rates, we actually see a peak. And this is what we've been looking for. So let's zoom in. So the right plot here is just a zoom in below the hyperon onset. So yeah, as I said, on this axis, we have bulk viscosity. And now you see the density range is just from 1.1 to 1.8. So this is really just this part here. And I've plotted again the bulk viscosity for various different temperatures. And what you see is absolutely what you expect. So you have a peak here, which means if I go up here, the rate gets slower and slower because I have less and less hyperons. The phase space gets smaller and smaller. And at some point, this is exactly where, if we go back, this line intersects this line. So we see this is right here. Of course, if I decrease the density more, I go further away from the hyperon onset, the rate will start to get too slow, and this is why I get this peak structure. And at one point, I basically don't have any hyperons anymore. I have to cut it off, this calculation here. Of course, if we now increase the temperature, what does increasing temperature mean? We have more higher thermal population, we have more hyperons, so we have to go even further away from the density onset at T equals 0. And you see this is for various different temperatures in a 0.5 MeV increment. So this is 2.5, 3, 3.5, and so on. And you see how this peak shifts further and further to the left, which absolutely makes sense. I have higher temperature. I need to decrease the density to find this ideal match of external frequency and reequilibration rate. What we also observe is that this peak height slightly moves down. So for higher temperatures, I don't get as much of bulk viscosity anymore. So finally, we want to translate this into energy dissipation times. And this is my most important plot of this talk, the message I want to give you. So the energy dissipation times, I explained this in the nuclear case, are of course low for high bulk viscosity. You see a definition here that we use or derived. So there's nuclear incompressibility plays a role, the hyperonic incompressibility in this case, but it's inverse proportional to the bulk viscosity. So what you see here is a contour plot again in temperature and density regime, and you get this diagonal structure. So this is, as we said, at high densities, we're getting really close to the hyperon onset. I have to reduce the temperature to also suppress the thermal population. If I increase temperature, I go up. I have to decrease the density, go further away from the onset to still get a sizable bulk viscosity, which translates to short dissipation time. So this is why you get this kind of valley here, which is 16 milliseconds, which is below this 20 milliseconds arbitrary cutoff we set at the beginning. And of course, let's say we start at an arbitrary point here in this valley where the matching is perfect. Once again, if I increase temperature, the rates are getting too fast and the dissipation times dropping quickly. If I decrease the temperature, the opposite is happening, and also the dissipation times are dropping. And in this gray shaded area, I don't have any, basically I have no hyperons. This is where we had to cut it off for our calculation. And whereas I said the rate is not highly dependent on density, this is true above the sigma, above the hyperon onset. Here it's exponential, so you see that if I increase the density at constant temperature, the same is happening. So I increase the rate, I increase the density, the rate will increase, it's getting too fast, so the dissipation time will get higher, bulk viscosity will drop. The opposite is true if I go to the left. So I just summarized this again. I think the message is the same. I just focus on let's just look at the plot on the right-hand side. So this is the minimal dissipation time I get at a given temperature. And you see, so this is always picked at the perfect density. And you see that it gets as low as 9 milliseconds. If I increase temperature, this is because, as I said, this peak height shrinks. So the minimal dissipation time I'm getting at these peaks now also goes up. And this is what you see here. So up to 5, maybe even 6 MeV, we see dissipation times below 20 milliseconds. And of course, this ideal density needs changes rather quickly with temperature, since the rate dependence is T cubed. So the last slide I wanted to show you is, of course, I've tried to convince you that bulk viscosity, hyperonic bulk viscosity might be important in this parameter range of roughly 2 times saturation and 0 to 5 MeV or 1 to 5 MeV. So Elias Most from the Frankfurt group, who is now in Princeton, was nice enough to send me this plot of his simulation. So this is now really in the equatorial plane of one of these neutron star mergers. Just look at one panel here. You can still see the structure. This was the first star and the second star. And this is 0.4 milliseconds after the initial merger. And this is the distance from the center of the 2 stars in kilometers. And this color coding on the left, so this is symmetric, would be symmetric. The color coding on the left is temperature. And you see most of the stars actually in this very temperature range of 2, 3 MeV here, which I showed you is quite interesting for us. And on the right, you see density. And we have to look at the color coding at the very right here. You see this color code is from 1 to 2 times saturation. So you see many parts of these mergers are roughly in this density range. And this changes slightly with over time, and it will heat up so the temperature gets higher. But at these very initial stages of the neutron star merger, where we have these high oscillations, it seems like the parameter range might be quite perfect for hyperonic bulk viscosity. with that, I just want to summarize. So I tried to explain why bulk viscosity is a resonant phenomenon and depends highly on temperature and density. I showed you that the hyperonic rates above the hyperon onset are too fast for a sizable bulk viscosity, but we still get millisecond dissipation times below the hyperon onset just because we have this thermal population that suppresses the phase space. And I tried to argue that these results are largely independent of the equation of state. What we need is some kind of stacked onset of hyperons. So there must be an onset of hyperons, and if they appear too closely, the rates might go up too fast and it gets more complicated. So of course, to really see if bulk viscosity is relevant in a neutron star merger, this is beyond the things I can do. We try to convince groups that do these numerical relativity simulations to incorporate bulk viscosity into their simulations. And then it would be really nice to see if we can actually determine the presence of hyperons in a merger from the gravitational waveform from this template and then measure it in a detector and compare it. Okay, that's basically all I wanted to say. Thank you so much for your attention. And of course, I'm taking questions.
Thank you very much, Alex. Very good. Well, I enjoyed your talk, and I am sure that everyone did the same. Okay, well, if there are some questions, please ask Alex questions or make your comments.
Actually, I had a question, but I don't know if anybody can hear me now. Yes.
Yes, I can hear you now.
Ah, okay. So can you show the figure with the times, this contour plot?
Sure.
Yeah.
This one?
Yes, yes. So what actually will happen with these contours after the hyperon onset, so to the right? So I see in the right bottom part, I see like a spread of your value, right? So how it will continue to the right?
So basically, I think since the rate and the bulk viscosity is, more or less constant here, we will go to like 100 seconds or so, and this will take over, and we have basically really high dissipation times for most of the rest of the plot.
Right, but in the right bottom part, these 16 milliseconds, for instance, the contour should close somehow.
Yes, this contour will close. Yes.
The
problem is, I'm ending my calculation. So at really small temperatures, the numerical noise also gets more complicated. So I cannot really finish this contour closing. But yes, this will be, if you go to smaller temperatures, this will become like more of an island structure for the innermost contour. Yes.
Yes, I think it will be quite like a sharp close, right? So we will not continue too far to the right. What would you expect? Thank you.
Yes. Other questions, please?
I have a question regarding, hi, Alexander.
Hello.
I have a question regarding your time tau dissipation.
Yes.
It is the local dissipative time, not the global one.
Yeah.
Yes.
So, and this, the figure, this contour plot figure shows that 16 milliseconds, this time equals to 16 milliseconds only in the very small density interval.
Yes.
So if you extrapolate this to the whole star, because you need to dissipate the large pulsational energy of the star, of the mergers. So does it mean that this effect, this hyperon bulk viscosity will not be effective? So for me, it's not obvious that the process which is effective in the very small density interval will be effective to damp the huge pulsational energy.
Sure. Absolutely. Good question. So this is what I tried to show with this plot. And of course, this now fully depends on which parts of the star Is it just a tiny part where this perfect match is happening? Then yeah, you will only really locally have some form of dissipation. What I think might be interesting also is if you have this strong bulk viscosity, I mean, this energy has to go somewhere, right? So it also means that you're gonna heat up these regions. So this might have a further effect. And this is something which also has not been taken into account. So if I understand correctly, the way they get temperature in this simulation is by using the equation of state, and from pressure, they calculate back to the temperature. And of course, if you have bulk viscosity, temperature might also, I mean, it must heat up at these regions. So I think, I mean, this region, of course, it is small, but you can always kind of find the right spot for temperature and density. So it seems like there's quite significant regions at the early stage where these conditions are met. But yeah, it depends on the simulation and of the equation of state. So to see if the damping is really significant, I think the only way is to incorporate it into these simulations. All I can say is there is a certain temperature and density range where it might be important. But of course, I mean, for us, it's nice to have a positive result and say it is important. But for this community, it's also interesting to know which effects are not important, right? Once everything heats above 10 MeV or so, it's nice to know that hyperonic bulk viscosity most likely does not play a role. So it's probably they even care more for the non-result than they do for the yes result.
I mean, it's in principle, it is possible to make some very rough estimate by considering just oscillating star and turn off the bulk viscosity of this size in the small region, and just to estimate what will be the global damping time for some mode for some mode, for example.
Yeah.
Just to have an impression about the real time scale when you integrate over the whole stuff.
Problem is, I think if you want to do this, you need to assume some kind of shape where density, these contours of constant density and temperature. And as you see, these early stages of the merger, it's not spherical symmetric. It's a real mess.
I mean to make some very, very rough estimate, just order of magnitude, because for me it's not obvious that the locally defined damping time is.
I agree. It's not obvious, and yeah, maybe one can do a rough estimate.
And will it be very difficult to implement this bulk viscosity into numerical code and see what will happen? So it's great job.
Yeah, I'm afraid it's really difficult. The problem is how these simulations work. They're really not. You're not calculating the chemical potentials, the particle fractions at every simulation step. You use the equation of state every couple of steps to go back and solve basically the inverse problem. And for bulk viscosity, as we saw, if we define it like this, we need to know the out of equilibrium chemical potential. We need to know the density and the temperatures at all time. Yeah, I know that the group of Risola, they have students working on this for a year or two now, and I don't know if they have published anything. I haven't seen anything recently. So it's certainly not an easy task to implement it directly.
But in any case, they should do this. They should construct a code which would calculate all the microphysics, all these chemical potentials, and correct numbers of particles of different kinds and so on. So it will be in line with, general trend.
I absolutely agree with you. They should, but I think it's hard. I know that there are groups trying to restart this. For instance, I think Niels Andersen in Southampton mentioned to me that they try to set up simulations that are for these late stages. I mean, of course, for the in-spiral, that's not super important. These approximations are quite decent, and we already learn things like the tidal deformability just from the in-spiral. But yeah, for these late stages, or the late stages, I mean the actual merger, maybe one has to change the way the simulations work completely, but I don't know if this is easy. I don't know much about numerical GR, so I feel bad to tell these people, just do it. I know they try, and yeah, it would be really nice for us to have that.
I see. Well, more questions, comments? Sergey?
Yes, I have maybe a question, because maybe probably I missed, but can you repeat why it's the bulk viscosity does not sensitive to the equation of state? Because it depends on a set of hyperons, you said. I mean, as I understand your talk, but it seems that on set should depend on the equation of state.
Yeah, it's probably misleading when I say it does not depend on the equation of state. Of course, it depends on the equation of state. My point was, do I get this ideal matching? All I want to prove is I get some form of sizable bulk viscosity, and I want to convince these groups doing numerical GR that they should implement it and look further at it. And I think that no matter what equation of state you use, you will be able to find a density and temperature regime where you get this ideal match of the external oscillation frequency and the rate, simply because, I mean, the maximum rate will always be similar. And this is what I tried to show here. They top out at basically the exact same value, right? So it might be slightly higher or smaller, but if you look at, where did I show this? If you look at this plot, right? I mean, the ideal frequency is much lower. You're missing it by orders of magnitude. And so this means for all equations of state at these high densities or temperatures, once you go above the onset, you will not get a good match and you will have rather low bulk viscosity. And also this feature that you suppress these rates below the onset is quite universal. So where this intersection might take place strongly depends on the equation of state. If you have hyperons appear only at much higher densities, yes, so this entire plot will be shifted to a different density and different temperatures. I agree. But no matter the equation of state, I think you will get some sort of sizable bulk viscosity, and the shape of the plot, this valley structure or island structure, will always reappear in some form. But yeah, of course, it depends on the equation of state in the sense where this innermost island will be. Absolutely.
Okay. More questions?
Also, I have maybe naive question, but the external frequency, it's come from the yes, okay. External frequency, it's come from in spiral phase, I understand. Yes, in spiraling or
no, we get the frequency out of these oscillations here after the merger. So the oscillation we're looking at are after the stars already touched. So
okay, but
unless you have an elliptic in spiral, you don't induce strong oscillations in these stars before they touch. So if they're just in spiraling and everything is spherical symmetric, basically you don't induce strong oscillations.
Mm-hmm.
okay.
Okay. More questions? So if not, let us thank Alex again. Thank you very much. Well, it was very good. Thank you.
Thanks again for the invitation. It was a pleasure.
Mm-hmm.
Thanks.
Thank you.
Yeah, goodbye. The seminar is over.
Thank you.
Okay. This time no questions from YouTube. Все понятно. Я забыл про эти осцилляции. Откуда они появились, вообще непонятно.